This video is about conservation of momentum. You calculate momentum by momentum equals mass times velocity. Notice it's velocity, not speed, because the direction matters. Let's look at a problem that involves conservation of momentum. Let's imagine we have two cars, both of them the same mass, 2 kilograms. One of them is moving towards the other with a speed of 3 meters per second, the other one is stationary. After the collision, they both stick together. When they stick together like this, it's called coalescing. We want to know the new velocity of the two cars. So to do this, we're going to use conservation of momentum. Let's work out the momentum before. That's going to be the mass times the velocity of the first car plus the mass times the velocity of the second car. Well, luckily, the velocity of the second car is 0, so the mass times velocity is also going to be 0. So our momentum is going to be 2 times 3, which is 6, and then I'm not going to forget my units. It's kilograms meters per second. So that's our momentum before. So by conservation of momentum, momentum before equals momentum afterwards. So we have 6, as we've just calculated. That equals the momentum afterwards. So the momentum afterwards is mass times velocity. Well, the mass is now 4 kilograms because they're combined together. So we have mass is 4 times the velocity. Well, our velocity is v because we don't know what the velocity is. I can then rearrange the equation whereby I divide both sides by 4. 6 divided by 4 equals v. So v must be equal to 1.5 meters per second. Well, that makes sense really, because the mass is doubled, so the speed must have halved. So let's look at a new problem, a one where the masses are not equal and both cars are moving. Do notice that the 3 kilogram car is moving slower than the 1 kilogram car. Has to be the case, otherwise there isn't going to be a collision, because it's not going to catch up with it. So again, we start with the momentum before. Just going to keep shorthand for mom for momentum. Momentum before. Work out the momentums and then add them together. So we have mass, 1 kilogram, times velocity, 4 meters per second, plus mass, which is 3 kilograms, times velocity, which is 2 meters per second, 4 plus 6, which equals 10 kilograms meters per second. So we have our momentum before. So by conservation of momentum, just writing it in shorthand for myself, by conservation of momentum, we have 10, the momentum before, is equal to the sum of the masses, because now they're coalesced, they're together, so 1 plus 3 times the velocity. So I'll keep rearranging and simplifying one step at a time. 1 plus 3 is 4, so 4 times v. So v must be equal to 10 divided by 4. Well, quarter of 10 is 2.5 meters per second. I can go on rearranging and working things out like that. Let's look at our last example now, but this time it's the mass that's unknown and not the velocity. So we're just going to approach it in exactly the same way. Momentum before. But this time I won't be able to find out an exact number. So I have the mass times the velocity plus the mass times the velocity of the second car. So in this case, my 2 times 0 will be 0, so I end up with 5m. Now I'm looking at conservation of momentum. So cons of mom. My momentum before is 5m, and that's going to be equal to the sum of my masses, m plus 2, multiplied by my 3 meters per second. Now at this point I need to do a little bit of rearrangement. I'm going to multiply through by 3, so I have 3m plus 3 times 2. Simplify that a little bit more. 3m plus 6. Now I'm looking, I have 5m on one side and 3m on the other, so I'm going to subtract 3m from both sides, so I get 2m equals 6, and then I'm able to divide both sides by 2, so m equals 6 divided by 2, which is equal to 3, and I don't forget my units, kilograms. I hope that's been useful.